Guest is Amanda Hendricks.
I'll show my title. It's going to be a slightly different title. Jeff asked me to fill in for Josh to talk about something involving UV. So I'll show you what we've been working on using LAMP data to study hydration on the moon. Okay. Okay, so what I'm going to tell you about is the hydration signature that we're measuring using LAMP and its diurnal variations. And as we accumulate more and more data, we see interesting variations in the diurnal changes in the Mare versus Highlands, and also we're seeing asymmetries in the signature strength before noon and after noon, and also in and out of the magnetotail. So as a reminder, LAMP is sensing very, very shallow depths of the regolith. Matter of fact, just sensing the top part of the epiregolith. So this is my little crude cartoon of the grains of the lunar regolith, the very top portion, to demonstrate that they're irregularly shaped, they're very rough and fluffy. So LAMP senses not even really into the grains, it's just sensing the outermost portion of grains, whereas an instrument like M-Cubed is sensing, you know, at least several grain sizes into the regolith. So that might have implications for temperatures and also even for the population of, you know, hydrating molecules that we're sensing. So we'll come back to that. So again, the reason that LAMP can sense hydration both in the poles and at lower latitudes is because of this strong water ice signature that is in the LAMP wavelength range. It's at about 165 nanometers. Also, thermal emission is not an issue at these wavelengths, so we don't have to worry about doing any corrections for thermal emission. So what we can do, and what we have been focusing on doing in this type of study is these are models of the lunar spectrum, a reflectance spectrum of the moon. If you look at the black line here, this is kind of a model of what we measure with no hydration. But because of that strong absorption edge that I just showed you, if you add just a little bit of H2O, and here we also assume we don't have a good lab measurement of just OH, but we think that OH, it's likely that OH could give a similar signature. But if you add just a little bit of such a strong signature, you can get a little change in slope here, right at around 165 nanometers. And if you add just a little bit more, you get a stronger change in slope. That's quite constrained in wavelength. And so you don't measure any difference when you add hydration at shorter wavelengths, and you don't measure any difference in slope at longer wavelengths. So what we have been doing is measuring the spectral slope over this very small wavelength range here, and looking at the distribution of the slopes all over the surface. What we have also done is measured as kind of a contrast or kind of a control, is measure the slopes over this longer wavelength region here, where we don't expect a change in slope, say with time of day or latitude. And indeed, we do not see a change in slope at these longer wavelengths with time of day or with latitude. But we do see a change in slope over the water ice absorption edge region with time of day and with latitude. And an example of that is shown here. This is beta angle, so it's essentially time of day because the morning angles are over here and the afternoon times of day are over here. Noon is in the middle. Up on the plot is redder slopes, so that would be consistent with an increase in slope. That's consistent with an increase in hydration. and lower on the Y scale is bluer slopes, consistent with less hydration. So what we see is that in the middle of the day, the slopes go very blue all over the surface, and that's consistent with the water going away at higher temperatures. At higher latitudes and early and late in the day, the slopes are redder, consistent with an accumulation of hydration at the colder regions. Okay. Oh, and also just to remind you, we did publish these trends here a few years ago using data through June of 2011, and this was what we measured at that point, and we continue to add in more and more data, and so here's a plot adding in a couple more years of data, and you can just see that the trend is holding up, but we're just filling in gaps in coverage. So let's think about compositional or terrain type differences. We can take a couple of, we're accumulating enough data now that we can look at chunks of real estate, say in a big highlands area, and compare it to a big mare region, and look and see what the differences are. And what we see here is that, again, this is local time versus our slope here. So less hydration down low and more hydration, or redder slopes anyway, consistent with more hydration towards the top of the plot. In both regions, we see that trend where the slopes are high, then they dip down and come back up. But in the mare region, the slopes are consistently lower than in the highlands region. Now, this could be due to composition, but we actually don't think so. These are some spectra of typical highlands and mare regions. If you look at the blue and cyan ones, those are a mature highlands and a mature mare region. So good for comparing with the regions I was just showing you. And in the 164 to 173 nanometer range, we do not see any big differences between those two areas here. It's just such a confined wavelength region that the bigger difference is due to composition of the two terrains come at longer wavelengths. So we do not think that largely these changes in slopes here between the two regions are due to the composition of the terrains. We think that it could be due to real differences in hydration. And this is actually consistent with earlier measurements from M cubed and epoxy showing greater abundances of hydration in highlands regions compared to mare regions. And also some of the results that Tom was just talking about where a highlands sample, this is the Michael Poston paper, a highlands sample seems to retain more water than a mare Apollo sample due to greater activation energies, as Bill Farrell has been working on. So that's one thing. The other thing about this plot here is that you can, the solid lines here kind of show the trend, kind of averaging the data in time bins. And what's interesting that we're noticing with more and more data is that the trend is pretty flat and drops off pretty suddenly approaching noon. And then as you head toward the afternoon, things ramp up a little more slowly. So this is an asymmetry around noon in the hydration signature, where you seem to get a steep drop-off approaching noon, and then it ramps up more slowly after noon. So this is kind of a new result, and we're working to understand it, but it seems like it could have to do with the mobility of the hydrating species, and that they tend to accumulate and desorb closer to noon, and then take a while to reaccumulate as the temperatures cool down after noon. This could be related to temperatures of the surfaces. Here we model the temperature of just these grains that are being sensed by LAMP, and if they really are, since they really are actually exposed to space, we expect them to have a different temperature variation during the day than the slightly deeper depths that are sensed by Diviner and the other instruments. So we may be sensing cooler temperatures, and perhaps even due to the roughness of the surface, slightly different distribution versus time in temperature. Can't really get this to work here. So it could be that we have a more peaked distribution, which is actually measured in some of these Diviner measurements, that could help explain that sharp drop-off as we approach noon. Okay. We can also look at the solar wind as a source of prompt hydration anyway, an immediate hydrating source by looking at a near-side region that is very often in the magnetotail. And so this is that Mare region that we looked at before. The red points here are, again, the slopes versus local time, and you can see the drop-off around noon and then the ramp back up. And what we have done is to look at the slopes also when that region is in the magnetotail. So we've looked at full moon plus or minus a couple of days, and thought that, well, maybe during those time periods we'll see lower slopes, bluer slopes. Maybe there's less hydration there, but we don't, actually. These black points here are the points where it's crossing through the magnetotail, and we don't really see an offset at all. So we think that we are not seeing hydration immediately being formed, but we must be seeing an accumulated effect in diffusing and migrating species. Here's another example where we can look at this region here in blue, which is always in the solar wind, and this region here is sometimes in the magnetotail. These regions are smaller, so there's fewer points, and it's probably hard to see, but the answer is that when this region here is in the magnetotail, we don't see that the slopes are any lower. Okay, so in conclusion, just to kind of summarize, the LAMP data is such a big data set that it's really rich for studying these diurnal lunar hydration trends. We see compositional differences with greater hydration levels in highlands regions, which is likely related to greater activation energies, and differences in changing hydration levels around noon. And again, we do not see hydration differences during magnetotail crossings, which suggests that LAMP does not detect the prompt production of hydration, but the effects of migrating molecules, and perhaps illustrates the importance of meteor streams as a source of hydration as well. Thank you.
We have time for a few questions.
This is really puzzling. Everything makes perfect sense until you got to this last part where there's no difference.
Mm-hmm.
And
I know.
okay, so can it be some geometry effect? Well, first of all, it's over just a couple of hours too. It's a relatively narrow zone.
Where that region is in the magnetotail?
Yeah, well, when you have the drop, it's only over a couple of hours rather than the broad kind of
yes,
thing.
it's narrow.
So that's one puzzle, but then the other is that you don't see any difference when you change some of the conditions. Can it be some geometry? You know, I was struck by some of your introduction where you pointed out you're looking just at the surface interaction and any fairy castle structure, something about illuminate.
Well, I do think that the geometry has to do with it. I don't think it's a geometric correction that needs to be made still. I think that we're seeing, the effects of that super fluffy and rough surface.
Okay.
And so there could be illumination effects that help water or OH or whatever.
See into it.
Yeah.
Yeah. Okay. Okay. That might make sense. Okay.
It looked like there was a drop-off too at dusk and dawn.
Okay. We don't believe that right now. We have the fewest amount of data points there So we just started thinking that it's basically flat and kind of saturated out. We need to add in more of those high beta angle observations.
I have no idea if this suggestion is going to be valid or not. But with Diviner, we measure relatively small temperature differences between the highlands and the mare at similar latitudes, just due to the albedo difference between them. But like you mentioned in your talk, we're kind of integrating over a deeper depth than you would measure. There are these there are thermophysical models. Bruce Joukowsky and Henderson and Joukowsky have kind of looked at these, temperature gradients you can get on airless bodies, and it might be interesting to see whether the surface temperature, the very surface temperature differences between, relatively higher albedo and lower albedo regions might be, something more substantial than we would measure, with Diviner, kind of more depth integrated, and whether that might have an effect on kind of water stickiness.
Okay, so you're thinking that the temperature differences in the mare and highlands could help to explain the hydration differences there too.
Maybe.
Yeah, I think, I don't see why not. But evidently the activation energies, let's see, Bill's work has been talking about temperature, the contribution of temperature and activation energy, and kind of the combination of those, if I'm getting that right. So yes, both are important, but we don't want to forget the activation energy. Good, thanks.
Great, let's thank our speakers.
Okay.
So at this time, I know we're keeping you from the light refreshments, but we have some time allocated for discussion. So if you had any questions you didn't get a chance to ask, or if there's anything you wanted to discuss on this session, now's the time.
Well, I have one question for Amanda. So is opening the door going to help get better?